We have seen in probability 1 that this statement x and y are independent. This means that probability x lies in B1, some set B1, and y lies in some set B2 that factorizes into the individual probabilities. The probability of x in B1 times probability y in B2. And this is true all subsets B1 and B2 of R. And as we have seen, we do not really work with all subsets, we work with only some good subsets of R. Now, if someone gives us two random variables, jointly distributed random variables, then it is of course not possible for us to check with all possible B1s and B2s whether this equality holds or not. So we have a little theorem which helps us to determine if two given jointly distributed random variables are independent or not. We start with two jointly distributed random variables. Then I am going to give you a necessary and sufficient condition of x and y being independent. X and y are independent if and only if the joint CDF, capital F x y, joint CDF of the pair x comma y, that factorizes as the marginal CDF of x and marginal CDF of y. And this must hold for all xy in R. If this condition holds, then they must be independent. Conversely, if these two are independent, then this condition must hold. The proof is pretty straightforward once you notice that this fxy is simply, by definition, probability x less than or equal to x, y less than or equal to y. Similarly, this is equal to this and this is equal to this. So this is same as this equality. Now if x and y are independent, I see that this event is made up of two parts, one in terms of x, the other in terms of y. So by independence, it will split up, factor out into the two probabilities, the x probability in one side and the y probability in the other. So if they are independent, immediately you get this. Now for the converse, you observe that if this condition holds, then once you have fixed CDF of x and CDF of y, you get the joint CDF. Now we know, we have stated, not proved, that CDF characterizes the distribution. So once you get the CDF, you get the distribution. We have already seen that if they are independent, then this will hold. And if this holds, then the CDF is same as in the independent case. Since CDF characterizes the distribution, so in this case, x and y must be independent. Now we can get a similar theorem for densities. So in this case, I will assume that x and y are jointly distributed, but with a joint density little f xy. Now what I shall do is, I can obtain this little f from this capital F by doing two partial derivatives. So once I partially differentiate this with respect to x, what do I get? This behaves as a fixed quantity because it does not involve x. The partial derivative only applies to this, where it becomes just usual derivative. So when you differentiate this, you get the marginal PDF. So this is del x. Now when you apply on top of it del y, partially differentiating with respect to y, this behaves as a fixed thing. This is now differentiated and becomes its density. So this quantity is actually our little fxy. So we get the characterizing property of independence in terms of joint density. So x and y jointly distributed with joint density little fxy. Then x and y are independent if and only if the joint density factorizes into the two marginal densities. If I have two jointly distributed random variables x and y that are independent and have the same density given by this, where lambda is something which is positive, then your job is to find the joint density of the pair x, y.